Hello and welcome to episode 16 of CS350 Online. I'm your host, as always, Leslie Eisted, and on today's episode, we're going to start a new topic, and that is the topic of scheduling. But of course, let's do the operating system of the day first. So today's operating system is the one and only DOS, which was released in 1981, and it's kind of a joint venture between Microsoft and IBM. Now, DOS itself stands for Disk Operating System, and it's actually not the first operating system to be called DOS. There was an older, unrelated operating system, which I would believe was released on the PDPs by DEC, that's digital, back in the 70s, but it's not really something we're referring to the Microsoft and IBM DOS here. So what happened was right just before 1981, IBM was developing a PC, the 1981 IBM PC model 5150, which I actually owned one, though not in the 80s. And they were looking for an operating system for this computer, this big launching computer. And they had originally planned on developing their own operating system called CP/M. But it wasn't ready for the launch of the hardware. And that's the thing, that they needed to make sure that they had an OS launch with the hardware. Not because the computer needed an operating system, it actually didn't, because it didn't ship with a hard drive. And it fully supported self-bootable games, which the majority of the games and software I had for the 5150 was a self-booting thing. It was very rare that I actually needed DOS. But IBM nevertheless wanted to release an operating system with the PC. So since theirs wasn't ready, they approached Microsoft and said, hey, Microsoft, can you give us an operating system for this hardware that we're about to release? And Microsoft said, sure, we can do that. And so they developed one. And by that, they purchased Seattle Computer Products and modified their operating system, which is where DOS came from. And then they sold it, or they gave it to IBM for money, obviously. Now, what's interesting about this is even though Microsoft developed this operating system for IBM or in partnership with IBM, and that's known as PC-DOS, which is actually the version of DOS that I have used the most, Microsoft continued development of DOS on their own and simultaneously released their own version. So PC-DOS is the IBM variant and Microsoft DOS is the Microsoft chain. What's interesting is that there's actually a bunch of other variations of DOS that exist out there. And when I was younger, I actually had a bunch of these, but I had no idea what they were. Like, I understood PC-DOS and I understood Microsoft DOS. But what is Dr. DOS? What is double DOS? Like, I did not know at the time. I still don't know what these were. Unfortunately, I no longer have the computer, so I can't fire it up and find out what they are. So what is DOS? DOS, as many of you may have experienced, maybe, is a very, very simple operating system. There's no multitasking. There's no GUI, anything like that, or at least there wasn't any graphical user interface provided until later, and really that was only provided as like an application through Windows. It wasn't like its own thing. It had a very basic file system, which is the FAT file system, which we'll be talking about in a few episodes. And it had a very restricted file size. It had a very restricted file name format, which is all a part of FAT. Very limited memory support. So the earliest versions of DOS actually did not use virtual memory. So that means they had direct hardware access, because they really did have direct hardware access. They didn't even have a separation between kernel and user, which is interesting. And it actually made running programs quite difficult, because if you had the wrong version of DOS or the wrong version of a program, it just didn't work. Like, I remember some of the early games in the DOS era. If you had a funky piece of hardware, it just wasn't going to work. I remember my 486, which is a computer from roughly the early mid-90s. It had It had a bizarre sound card and like some off-brand sound card, and because it was so off-brand and so weird, and because of how DOS having direct hardware access worked and the limited abstractions that DOS provided, I never had sound in games, and getting sound in games required me to actually tinker with some interrupts in the Windows 3.1 driver. Did get it working occasionally, but there were some areas where you couldn't get it to work. Now it is a command line interface, so you are going to have commands like cd, and you're going to have commands like mkdir and I haven't used DOS in so long, rem to remove a file and so on. But I mean, it does provide you some ability to do batch scripts. But it's not really a sophisticated operating system as a whole. What's interesting is, so DOS has been around since 81, and all of the variations of Windows up to and including Windows ME are actually built on top of DOS. But anything in the NT family and any modern version of Windows is actually not built on DOS. So Windows 95, totally built on top of DOS. Obviously quite a bit extended on top to provide a little bit of virtual memory and so on, but still very, very limited. And Microsoft eventually kind of dropped the DOS line of Windows to go to the NT line, which was a lot more stable and had a lot better support for things like concurrency and so on. But we'll talk about Windows another day. I thought it would be fun, however, to show you one of my favorite DOS games, and it's a classic, and you can play it in your web browser. It's called Castle Adventure. And we can just, sort of, I wanted to go full screen, but it doesn't want to let me. It's called Castle Adventure. It's very, very silly. And, I mean, this is the kind of graphics that you would expect. It's ASCII-based graphics. So this is all rendered. And you'll note here that we've got the club sign because it is, it's the extended ASCII character set. So you've got, instead of 128 ASCII characters, you've actually got 256. And this is such a classic game. So you're this little club shape, and you're in this castle, and you're trying to get all the treasures and escape out of the castle. And as you're exploring the castle, of course, you're going to encounter monsters. And in order to kill the monsters and proceed, you're going to have to collect things like swords and shields. And you can only carry a limited number of things. It's a really fun game. And I actually had this for the IBM 5150. Unfortunately, the game was actually corrupted, which was really interesting because there were actual bugs in the game because there was a corruption. And so you could actually escape the castle without actually escaping the castle. But the monsters were also super aggressive. So yeah, this is a fun DOS game. And if you're interested, you can actually find... there, I died because of an ogre. You can actually find a lot of these games available on the internet for download on things like abandonware websites. Some of them you can even play in a web browser, and they're lots of fun. This game is actually surprisingly tricky, especially considering that it's really, really old. All right. So, it's time then to move on to a new topic, and that is the topic of scheduling. So, the things that we've covered so far, threads, processes, and synchronization, we've talked about virtual memory. But anytime we talk about a context switch, we've completely ignored how do you actually choose which thread goes next. And arguably, maybe we should be discussing this when we talk about threads and processes, but we've been saving it until after virtual memory. That, by the way, usually has to do with the ordering of assignments. So the question is, how do you choose which thread goes next? Is it okay to choose just any thread to go next? Or are there other considerations that we should be thinking about when we're trying to decide which thread goes next? Things to keep in mind are the fact that you want to make sure that your users are under the impression that all of their programs are making progress, even if they are not technically running at the same time. So you don't want to give your user the impression that if you've got two YouTube windows open, but the two YouTube videos are taking turns playing, you want them to both appear to play at the same time. You don't want your user to believe otherwise. So we've got to handle things like, how do you think about creating fairness between those threads? And you've got to think about, well, what happens to threads that have fallen asleep and we've woken them back up because whatever resource that caused them to fall asleep is now available? Should we treat those threads any differently so that they can maybe respond quickly to the fact that an event has occurred? And all of those things come into this kind of scheduling discussion. So let's then look at scheduling. We're going to start, by the way, by going kind of back in time and talking about scheduling from the perspective of jobs. So let's ignore threads and processes for a few minutes. And let's talk about jobs instead. So this is kind of the way that you would have seen scheduling happen in the 1950s. So you've got a bunch of jobs that you need to schedule. And you know that you can only run one job at a time. So we're going to ignore the existence of multi-core machines or multi-CPU machines until the very end. And then we'll talk about how to modify all of these methods to work on a multi-core system. But let's suppose you can only run one job. Now, for each of these jobs that you have two pieces of information that you've been given. What time the job arrived in the queue, and number two, how long it's going to take for that job to run. So a job arrives and the job is going to say, I arrived at, what time is it? 9:46 a.m. and I'm going to take 5 minutes to run. So there are some metrics that we can use with respect to these jobs. We can define the response time. That's how long does it take from the time the job actually arrives and the job actually runs. So how much of a delay does it take before the job actually gets to go? And then the turnaround time is the time it takes from the moment the job arrives to the moment the job finish runs. So that means the total time it takes for that job to complete from the time it arrives. And when we're thinking about scheduling algorithms, for now, what we want to do is minimize the average of one of these. Either we want to minimize the average response time or minimize the average turnaround time. We're not, by the way, going to do any proofs of this. It's 350, not 341. So there's lots of different techniques that we can use. And this is actually the easiest one here. So this is first come, first served. So the idea is that you have a ready queue, and as a job arrives, it goes to the back of the queue. And then we always choose the job that's at the front to run. And so in this case, we have this set up where we have 3 jobs at time 0 have arrived. And we're going to assume they arrived in the order J1, J2, J3. And we have their run times here. Although for first come, first served, the runtime doesn't actually matter because we're not using the runtime as a means of deciding who goes next. We're using your arrival time to decide who goes next. So job 1 arrived first, so it gets to go first. It finishes, of course, at time 5. And so at time 5, we run the next one in the list, which is going to be job 2. It runs for 8 units, finishing at time 13. And then we run job 3, which takes 3 units. And then job 4 actually arrived all the way back here at time 5. But when the new job arrived, it went to the back of the line, so we can't actually run job 4 until all of the preceding jobs have actually completed. So job 4 doesn't actually run until time 16. Now, if you're wondering what this time unit is, it's just an arbitrary unit right now. We're not going to worry about it. Okay, first come, first served. So what are some advantages of this? Well, some advantages of this are it's very easy to implement, obviously. It doesn't really require any thinking. It's another interesting advantage is when it comes time to choose the thread that goes next, there is almost no work to be done. You don't have any complicated algorithm to decide, well, maybe this other thread should go first, or maybe we should let this thread go. You don't have to do any thinking. You simply take the one off the front of the list. So it's really, really efficient in terms of its implementation, and it's really simple to implement. One of the other really big benefits of first come, first served, it doesn't have any starvation. What that means is you don't want a job to arrive and never end up running. Every job that arrives to first come, first served will end up running at some point, and we know this. Now, this, of course, is making the assumption that jobs actually terminate. We'll talk about that in a little bit. The other thing I would argue is it's kind of equally fair to everybody. Everybody has to wait their turn. Maybe that doesn't create the world's greatest experience, though, because things like job 4, which are really, really short, have to wait a really long time before they might run. So this is first come, first served. Now, another downside of first come, first served is the fact that jobs truly go one at a time. So if I had 2 Chrome tabs open and I was watching a video in each of them, let's say in one Chrome tab, I'm watching a YouTube video about Breath of the Wild 2 theories and conspiracies. And in the other Chrome tab, I might be watching some of the cutscenes from Final Fantasy VII Remake. Okay, that might be my real YouTube history. Maybe I'm very odd and I want to watch those 2 videos at the same time. But with first come, first serve, that wouldn't happen. The entire Breath of the Wild 2 conspiracy or theory video would play. And then, once it's completed, the Final Fantasy VII Remake video would play. So I don't get that feeling of 2 things running at the same time. But as it turns out, with a teeny tiny modification to first come, first served, you can get that concurrent feeling. And this is actually what OS 161 does. So I'm going to take this over into my notebook here, and we'll actually draw out what happens. So this is first come, first served with preemption. So now we're going to have a scheduling quantum, and in this case, we're going to use a scheduling quantum of 2 units. And so what happens then is when you're still always going to choose the job from the start of the queue. And when a job arrives, it goes to the back of the line, but there's some additional information. When a job gets preempted, it goes to the back of the line. So pretty much the answer to everything is go to the back of the line. So let's go over here. And I've got to make sure I've got the right job lengths. Grab that for a minute. So you can see there at the bottom of my screen, there are the 4 jobs, their arrival times, and their run lengths. And then what I'm going to do over here is I'm actually going to write this out. So at time 0, apparently I have a bunch of, Don't you love it when applications crash? All right, so at time 0 then, this is my, not a ready pool, but we're going to call this my ready queue. And at time 0, I have the following jobs in my ready queue, and I'm going to draw each of the jobs with how much runtime they have left, just so you can kind of follow what's going on here. So you've got job 5 with 5 units left, job 2 with 8 units left, and we have job 3 with 3 units left. So at time 0, we choose a job to go. We always choose the one at the front of the line, which means we're going to choose job 1. Now, our quantum, remember, is 2 units. So job 1 wants to run for 5 units, which means it's going to get preempted. And then at time 2, because it gets preempted, job 1 is now going to go to the back of the line. So now our ready queue at time 2 looks like this. And you will note that I've updated the amount of time left to run on job 1 so you can see exactly how much progress that particular job has made towards its completion. So at time 2, I have to choose a job to run, and I'm going to choose the one at the front, as always. So I choose job 2. Now we know that job 2 wants to run for a really long time, so it's going to get preempted 2 units later at time 4. And at time 4, my queue looks like this. Trying to write as neatly as I can so everybody can read it here. All right. So job 3 is going to get selected at time 4, and it's going to get preempted at time 6. However, at time 5, and you'll notice I'm writing this in a different color. So job 3 is running, but job 4 arrives at time 5. And at time 5, then, our ready queue is going to look like this. There we go. And so then at time 4 or time 6, when job 3 gets preempted, our ready queue is going to look like this. And you'll see that we actually have job 4 in the list, and you can see where it came from. And then we choose, of course, job 1 to run again because it's at the front of the line. And this is going to keep going. So then this gets preempted at time 8. And then we'll select job 2 to run again. It gets preempted at time 10. And then at time 10, we select job 4. Now, what's interesting about job 4 is it runs for exactly 2 units of time. So it doesn't actually get preempted. It terminates 2 units of time later. And it leaves the system altogether because it's completed its entire job. And then, of course, we're going to select job 3. Job 3 terminates before the quantum expires, which means we need a new job to do at time 13. And so we're going to select job 1, which terminates before its quantum expires as well. So we need a new job at time 14. And the only one left in our pool is the lovely job 2, which will also get preempted at time 16. And then at time 18, all the jobs will have completed. So that is round robin scheduling, which is the preemptive version of first come, first serve. And this is actually what OS 161 does for its scheduling. It is still incredibly simple to implement because you still just have a ready pool. And now when jobs are getting preempted, they just go to the back of the line. They go to the back of the ready pool. You can implement it as a basic queue. So aside from giving us this feeling of concurrency, there's also an additional advantage to this particular mechanism as opposed to just first come, first serve straight up. One of the problems with the previous method we showed, the non-preemptive one, was that what happens if a job blocks? It needs to wait for some other job to do something for it. Well, with that, first come, first served would actually not work very well at all. In fact, first come, first served straight up doesn't take into consideration the fact that jobs can block. Whereas it's not really a big deal for this preemptive model, because what we can do is at the point where a job blocks, we have a context switch and we can simply push that job to its sleep state, and then when it wakes back up, we just put it on the back of the line. So this handles it a little bit better. All threads, or all jobs in this case, are also treated equally. All right. The question becomes, can we do better? So there is another really old idea for scheduling jobs called shortest job first. And the idea behind shortest job first is not that we're going to serve the jobs in the order that they arrive, but we are always going to serve the jobs that are faster before we serve jobs that are slower. So in our example here, we've got the same 4 jobs again, and they arrive, all 3, J1, J2, and J3 are all there at time 0, and then job 4 comes in at time 5. So at time 0, we choose the shortest job to go first, and that's going to be job 3. And then when job 3 is done, then we choose the next shortest job, which is going to be job 1. Now, while job 1 is running, job 4 arrives. So when job 1 is done, we run job 4, and then finally we run job 2. The advantage here is this actually is going to minimize the average turnaround time, because we're going to be giving a preference to running short jobs over long jobs. And if you actually look at your system, the majority of the jobs that are being scheduled would be very short. So you've got lots and lots of really short jobs, and you want to serve them before you serve any really long jobs. But here's the problem. You can get starvation pretty easy. And how it arrives is jobs are constantly arriving in the queue. And if long jobs are really rare and short jobs are really common, and short jobs are going to be arriving at a rate faster than, so they're always going to be served first. You can kind of think of it this way. It's common courtesy that when you show up to a grocery store, and let's suppose you're in line, and you've got 2 grocery carts full of shin ramen, the spicy one. And somebody shows up behind you and they have 1 loaf of bread. Well, courtesy dictates you let them in front of you. So you let them in front of you. Well, that's this example here. But here's the problem. Most people don't have 2 carts of shin ramen. Most people have just 1 or 2 items, and that's it. So one person shows up with 1 loaf of bread, and you let them in front of you. And then another person shows up before you get served, and you let them in front of you. And the problem is with shortest job first is there's a never-ending lineup of people showing up to you who have less things in their cart than you. So you, being a courteous person, keep letting them in front of you. And then what ends up happening is you starve to death in the grocery store checkout with 2 carts full of ramen noodles. We don't want that to happen. We don't want there to be some job on your computer that gets starved, because that's like opening VLC and trying to play a video, except guess what happens? Nothing. We don't want that to happen. That would make you very angry. So shortest job first may minimize the average turnaround time because it does prioritize those really short jobs, but you can starve. Now, the next question is, can we add preemption to make this better? There's a question on Twitch here. How does the scheduler know how long each job will run for? I'm not going to address that question right now, but I will address it in a couple minutes. So please be patient. But we will address that. All right, so can we use preemption to improve shortest job first? And this is a variant called the shortest remaining time first. And the idea is that, and there's a few ways that you can implement this, but one of the common ways is, excuse me, when a new job arrives, we preempt the running job and then choose the job that has the shortest remaining time to go next. So what I'd like to do is go back out to OneNote here, and let's redo this again, except let's do this with, stupid program keeps crashing. All right, so let's redo this with, it appears to be some kind of weird render problem. That's annoying. There we go. It's probably Microsoft telling me I don't like the fact that you're running my products on macOS. Anyways. All right, so instead of a ready queue, we have a ready pool. And at time 0, and again, I'm going to keep track of the remaining time with each of the jobs. We have job 1 has 5 units left, job 2 has 8 units left, and job 3 has 3 units left. Now for shortest remaining time first, we're going to choose the shortest remaining time, which it means that we're selecting job 3 to go first. Now it's going to run to its completion because no jobs arrive in those first 3 units. So at time 3, my ready pool looks like this: job 1 and job 2. And in this case, my shortest job here is going to be job 1. Now at time 5, the system gets preempted because a new job arrives. So my ready pool now looks like this. And the new shortest remaining time job is going to be job 4. So it's going to get to go. And it completes at time 7. That's not a 7. Yeah, like it totally won't let me erase. Anyways, time 7, we have job 1 with 3 units left and job 2 with 8 units left. We're going to select job 1. It's going to run to completion, and at time 10, we have just job 2 with 8 units left, and we're going to select it. So we did get a little bit better handling of shorter jobs arriving. We were letting them in front of us. We're even letting them interrupt us and run while we patiently wait by the sidelines. But it still doesn't quite give you the feel of 2 programs running at the same time, and it also still really, really suffers from starvation. Now, there's an additional problem with these 2 methods to address the question that's posted on Twitch here. And that is, how do you know how long a program's going to run for? Because in reality, we're not talking about jobs, we're talking about threads. And I don't know about you, but when I sit down to use a program on my computer, I don't know how long I'm going to be running it for. If I sit down and I tell myself I am only going to play Red Alert 2 for 30 minutes, there is a very high probability that 16 hours later, I'm still playing Red Alert 2. Saying that from experience. So if we don't know how long we're going to run the job for, then how could the computer or the scheduler know how long the job's going to run for? And you might be saying, well, we could collect metrics about how long people use this program on average, and we could use that to estimate and, build models and... Okay, machine learning for scheduling, it's not that it's impossible. It's not that we haven't used machine learning for scheduling. It's just that that seems really inefficient. We want the selection of the next job to be as quick and easy as possible. So maybe doing ML is not right for this. But there's other problems with this. Aside from us not knowing how long the job is going to take, even if we did know theoretically how long the job should take, that doesn't mean it takes every computer the same amount of time. Now, an example I've used before, except in processes to describe the effect of system calls, was when I was first learning to write programs. One of the first basic programs that I wrote or I worked on, it's a stupid little program, was to print the numbers from 1 to 1,000,000 on the screen. And we did this on a Commodore 64. This is a very easy piece of code. But on a Commodore 64, that simple piece of code took 12 and a half hours to execute. The speed at which your program executes is dependent on the hardware that you have in your system. 12 and a half hours on a Commodore 64, it only takes a couple minutes on my computer here. Now, there's other things to take into consideration too. It's not just what hardware you have sitting in your computer right now. There's other things to consider as well. You have an operating system. The operating system is receiving events and signals from the CPU. It's handling interrupts. It's handling system calls. You don't know all of the things that are going on underneath in the kernel of the operating system while your job is running. And what's interesting is each time you run your job, what's going on at the operating system level may differ. There may be different interrupts that get fired, different internet packets that arrive. Those are all interrupts. Let me demonstrate this for you so you can see just how hard it is to know how long a job will run for. So I have a very simple program. You should also read that as very boring program. Oh, that's the wrong name. So here's a very simple AS. It's a C++ program. So we've got a loop here, and inside the loop, it's adding and it makes a function call that does another loop. So we've got some nested looping and function calls going on here. This program doesn't do anything real. So what I'm going to do is there's actually a command you can use to time how long it takes for a program to run, and that is time. So let's actually time how long it takes to run this very simple little job here, this little program. There we go. Don't worry about this negative number. The answer doesn't matter. This was simply, I wanted to write a program that takes some time, does some computation. So here we go. Here is an analysis of how much time it took to run this program. You can see here there are 3 different values used. Real is how much time you perceived this job to take to run. So it says it took about 5.653 seconds. Now you'll see there's actually a breakdown here. It spent 5.568 seconds approximately actually executing the user program that is actually running this code. And it spent about 0.054 seconds executing system code. It's kind of neat, right? You can actually break down how long programs take into how much time they actually took and how much time the operating system spent doing things. Now let's run this again. And I think you'll both, everyone who's sitting there watching this, you'll all agree that I haven't touched anything on my computer since I ran this program. So let's run it again and see what happens. It takes a few seconds. There we go. Now, I did nothing different. And yet the program took a different amount of time. And I could run this again and again and again, and I won't get the same runtime. So knowing how long a job is going to take is almost impossible. Because number one, you don't know how long you're going to run the program for. It's dependent on the hardware, the speed at which we can actually execute instructions, the speed of our memory, and it's also dependent on what else is your computer doing right now. Now, if you're wondering, what's going on? Why was this so different for 3 sequential runs? Well, the things that you're not taking into consideration is I'm streaming, and that means I'm sending data out over my network. That network is going to take some power. It's going to cause some interrupts, so I'm handling some interrupts here. You'll actually note that on the 3rd run, I did a little bit more kernel work than others. You're also not taking into consideration what other threads might be running on the machine, the scheduling, how do we make it fair? This is not a very user interactive program, and so it's actually going to get not as much priority as something like Chrome. All right. So at the end of the day, things like shortest job first and shortest remaining time first, they're not really practical in reality because we don't know how long jobs run for. If you're wondering what that sound is, by the way, it's an impact drill. All right. So if we don't know these things, so we have another question here. How does time differentiate between the system and user code to get those numbers? So I don't know the exact implementation of this particular function. If I had to take a guess, though, it's probably a set of system calls. And when the system calls operate, it's probably going to start a kernel counter, and it's going to count. And I mean, this is just a guess of how I would implement it. It would be a system call to say, hey, start counting the time that you spend in kernel privilege mode and count the time that you spend in user privilege until the user process terminates. That's how I would do it. Again, that's a really system-dependent implementation. All right. So if we can't know how long things are going to run, then things like shortest job first don't make sense. First come, first served and round robin still work, though, because they didn't care how long things are. But then there's some other things that we need to take into consideration, such as do we want all threads to have equal priority? Think of it this way. On your computer right now, if you're watching the live stream, you're watching Twitch, and that would mean that that's a very interactive program. You're constantly receiving data from the internet, and you actually want that to be a very responsive program because nobody likes lags or having to have pauses in the video, or nobody wants to have downgrades in video quality. But if you are simultaneously downloading something off BitTorrent, you're not sitting there watching the bits come in on BitTorrent. You don't care. You just want to know that when it's time to eat your supper, that you have a movie to watch with your meal. So should we treat all of these threads equally or not? How do we ensure that our responsive threads get more time than our threads that we don't expect to be very interactive? How do we ensure that we're also being fair and ensuring no starvation? How do we ensure that our methods are being efficient? So what I'd like to do now is actually look at some real scheduling algorithms. And the first one, you'll see here in bright red, is the most commonly used scheduling algorithm in modern times. And it's called multi-level feedback queues, MLFQ. And this is used by Windows, it's used by Apple, it's used in Unix, things like BSD and Solaris. It used to be used in Linux, but they have their own scheduling method now. And it's not to say that all of these operating systems are using the exact same implementation of MLFQ, but they are all based on the same idea with their own variations specific to their kernel of their operating system or whatever goals they have. So the idea here is we want to make sure that threads that are interactive have snappy responsiveness. So for example, if you're playing a first-person shooter like Unreal, which is one of my favorites, you want to make sure that you're getting a really snappy response because nobody wants to play a video game at 1 frame per second. And I have done that before, and it sucks. And if you're wondering what game it was Warcraft 3, and I was playing it on a computer with an NVIDIA Riva TNT2 graphics card. 1 frame per second might be generous to say what I got. I bought a new computer, obviously. So we want to make sure that any kind of interactive thread, that is threads where they're going to block frequently to wait for user input or packets from the network. So things like Chrome, when you're running YouTube, it's waiting for packets from the network. We want to make sure that those threads that are going to block frequently we're very responsive to when they become unblocked. That is when their resources become available again. But how do we know when a thread is going to be an interactive thread or not? Because the kernel of your operating system doesn't know, oh, this is Chrome, and it's running YouTube. Your OS doesn't know that. Your OS doesn't care. So how are we going to figure out kind of on the go which threads are interactive and which are not? So that's where this multi-level structure actually comes in. So instead of having one ready queue, and all these queues, by the way, are doing first come, or essentially first come, first served, but you're going to have multiple ready queues. Now, the highest priority, each queue is going to have a different priority. The highest priority queue is Qn, and the lowest priority queue is Q1. And what's interesting is we're going to set the quantum for each of the threads in each of the queues different. So the highest threads that are in the highest priority queue get the shortest quantum, and threads that are in the lowest priority queue get the longest quantum. And the idea is when we want to select a thread to run, we always choose the thread from the highest priority queue that has threads in it. So it will first check Qn. And if Qn has a thread, we'll take it and run it. And if Qn doesn't, then we'll look at Qn minus 1. And if Qn minus 1 doesn't have anything, then we'll look at Qn minus 2. And so on. Now, why does this work? So what's to find the interactive threads? So here's the other part of the idea. How do you go from Qn to Q1? Well, what's going to happen is high priority threads have the shortest quantum. If they get preempted, then we make the assumption that because you got preempted, you're not as interactive as the other threads that are in the high priority queue. So when you get preempted, you're not going to go onto the back of the queue you came out of. You go into the back of the next lower priority. So if you are a thread running from Qn and you get preempted, you go onto the back of Qn minus 1. And if you're in Qn minus 1 and you run and you get preempted, you go into Qn minus 2. And the idea is that threads that block frequently won't end up getting preempted. Because what's going to happen is when a thread wakes up, it's going to go back into Qn. So any thread that blocks frequently and is therefore very interactive is going to go between Qn and the sleep state. And it's going to stay in that high priority, constantly being serviced. Whereas if you get preempted, that means that you don't block as often, or you are a longer running thread that doesn't block as often. So we're going to put you in a lower priority queue. Now, you might be wondering, well, what happens if I have no threads above, and the only thread I have is in Q1, the lowest priority, and it has, like, let's say a 500 millisecond quantum. What happens if a high priority queue thread arrives, a brand new thread, because every thread is going to start out in Qn, or let's say a thread becomes unblocked, so it's going to jump into Qn. Does that higher priority thread have to wait for the low priority thread to finish? Depends on the implementation, but most implementations of multi-level feedback queues simply state that if a lower priority thread is running when a high priority thread arrives, we will preempt the lower priority thread so that we can handle the higher priority thread. So we can preempt these slower or these longer running threads to let the higher priority, potentially interactive threads be super responsive. So here's just a 3-queue example. So we've got the high priority queue is 3, and then we've got a Q2 and our low priority Q1. And you can see here, when you wake up, you go you go into the high priority. If you run and are preempt, you go down. So lower priority things, less interactive, will trickle down to the bottom. And once you get to the bottom, you're just going to sit there and cycle in the bottom. Now, this actually raises an interesting problem. You'll note that this can starve, because a ray tracer, for example, is a lower priority thing, probably. And so it's going to sift down to the bottom because it's not very interactive. So when does it run? If I'm watching YouTube, and I've got like 6 YouTubes open here, when does my ray tracer ever run with this model? Well, the answer is it probably wouldn't, because it would be completely starved by the existence of higher priority threads. So, in order to prevent that starvation, what happens is periodically you take every thread in the whole system and you put them back into the highest priority queue. So, on Solaris, they actually had 6 levels with quantums ranging from, I think it was 40 milliseconds to 200 milliseconds. And once per minute, they take all of the threads in the system and put them back in the high priority queue. And that prevents the starvation. And this method is also fairly straightforward to implement. So here's a very brief example, kind of tracing you through what's going on. So we start with the system. We've got 2 threads in the high priority queue. And so we're going to, each of these queues is first come, first served. So we're going to choose T1 to run. So T1 runs and it's preempted. On its preempt, it goes down into Q2 because it's obviously not as interactive. And then we choose on that context switch, we're going to choose thread 2 to run next because it is the highest priority thread in the system. Now, while T2 is running, T3 arrives, but T3 and T2 have the same priority, so we don't need to do any preemption here. T2 terminates, and we need another thread, and you'll note that we're going to choose T3, not T1, even though T1 is significantly older. We choose T3 because it is a higher priority than T1, and we always choose the higher priority thread. When T3 blocks, it goes into the sleep state, and at that point, since there are no other higher priority threads in the system, we end up selecting T1 to run. When it gets preempted, it gets pushed into the next lower queue. So it went down in priority further to the lowest. And since there are no other threads alive in the system, it will get to run here with a longer quantum. Now, maybe T1 and T3 are actually threads of the same process. And maybe T1, while it was running this time, ended up unblocking T3. So what's going to happen is T3 is going to go into immediately the high priority queue, and T1 is going to get preempted, and so it's going to, since it's already at the bottom, go back into Q1. Now we have to choose a thread to go on this context switch, and the highest priority thread in the system is T3, and so T3 gets to run. And that is a way that we can actually make sure that we are being very responsive to events actually happening, is we give threads which are responding to wake-ups or just being new, a higher probability of running right now than threads that are less interactive. All right. So that's kind of, and I want to really stress that each operating system has made many, many variations of this. For example, in things like Windows, you can actually set the priority of some of your programs, which can actually have an impact on which queues that program lives in. For example, if you were to set the priority of a thread to a high priority thread, one of the ways that you can implement that is just say, okay, this is a high priority thread. I'm only going to let it live in these few high priority queues. So even if it keeps getting preempted, instead of traveling all the way down to the bottom, it has like a limit for how far down it can go. So there's some really interesting variations you can do for multi-level feedback queues. Okay, so what does Linux do? So Linux used to do multi-level feedback queues, and now it does something different called the completely fair scheduler. Now, something I want to say is that this is an exceptionally high-level overview of it, of the basic mechanism. There's actually a lot more to it, and you're welcome to look up the details. It's in a paper to see how it's actually implemented. We're just going to look at the high-level ideas. Question on Twitch. Roughly how many queues would there be in something like Windows or Mac OS? Like 5 or dozens? So I don't know specifically how many Windows has. I know that Solaris had 6, and Solaris was a BSD variation. So I could imagine that Mac OS probably has somewhere around that number. I don't know specifically. But Solaris, which is a BSD variant, had 6. So you're not looking at A lot of these. And someone else here on Twitch is saying that Windows has at least 9 priorities. That's more than they used to have, actually. They used to have only about 5, so they've really expanded that then. Admittedly, I haven't done anything with priorities of threads in Windows in a very long time. All right. You're not looking at things like 20 or 30 because that becomes a management nightmare. We want scheduling to be efficient, remember. All right. So what does Linux do then? So Linux does something called this completely fair scheduler. Now, multi-level feedback queues, you'll notice we said that there is, for multi-level feedback queues, you have a different scheduling quantum per priority. In Linux, we're not going to have varying scheduling quantums. Every quantum for every thread is the same. But instead, what we're going to do is we are going to assign each thread a weight. And then we are going to share the CPU's time proportional to your weight. So if you are a high weight thread, you should get more of the CPU's time than a low weight thread. And thank you to you Quarantine Lou for linking the wiki article on the number of priorities for Windows. That's great. 11 is a pretty good number of queues, actually. That's actually quite a bit. It's quite a bit more than they used to have. All right, so how does this work? How do you share the processor according to your weight? So what they're going to do is Linux keeps track of the actual runtime of a thread and the virtual runtime of the thread. So the actual runtime is how long has this thread actually run? Like actually run. And then the virtual runtime is the runtime adjusted for the weight of the thread. And we're always going to choose the thread that has the lowest virtual runtime to go next. So there's a little formula here, and I'm going to switch over to OneNote to do this, and hopefully it doesn't crash on me again. Probably will. So let's just scroll down. So I'm going to draw a line here. I drew one line and it drew two. I love it. So what we've got then for this virtual runtime formula is the virtual runtime. So this is a weight adjusted amount of time that a thread has run for. Is going to be the actual runtime, how long you have actually used the CPU for, multiplied by the sum of all weights of all threads in the system divided by your weight. So for example, if your actual runtime is 5, and I like to abbreviate this to AR, and the sum of all weights is equal to 100, and your weight is equal to, let's say, 20, then the virtual runtime for you would be 5 times 100 over 20. So this is going to equal 25. So that is your virtual runtime. And then we would, after computing the virtual runtimes for all of the threads in the system, we choose the thread to go next that has the lowest virtual runtime. And what ends up happening is threads with higher weights their virtual runtime is going to advance at a much slower rate than a thread with a high or with a low weight. So if you look at this here, so I did a weight of 20. We could have done a, I don't want to open resolve. We could, if we had a different thread with, say, a weight of 1. So if your weight was equal to 1, then your virtual runtime for the same AR and all weights be 500. And so if you get 5 units of more time to run, so let's say now you've run for 10 units and the other thread has run for 10 units. So this thread, the black one here, is going to, after 10 units, it's going to have a virtual runtime of 10 times 5 or 50. But if you've run for 10 units with the low weight, then you actually have 10 times 100. So your virtual runtime is now 1,000. So we're going to have higher weight threads have their virtual runtimes advance more slowly, which means that they have a higher probability of being selected more often. And it's not to say that we're going to starve out these low weight threads. It's just that we have to wait for the higher weight threads to get enough CPU time such that their virtual runtime is now greater than yours. And by the way, you can actually adjust the weight of threads in Linux using the nice command, which is kind of fun. And I think it's got like, so I haven't used nice in a very, very, very long time, but there are, I think, at least 22 weights for it. It's been a long time since I used nice. So just a quick example here. It's in your notes. So we've got a system where we have the total weight of all the threads in the system is 50. You can see that here's all the living threads. Their total weight is 50. And they have all run for 5 units of time. So we want to know what is their virtual runtime and which thread would go next, and then what would be the virtual runtime for the next step. So if we actually go on to the next slide, is the answers. So again, you're multiplying actual runtime by the weight of all threads divided by your weight. So in this case, thread 1 is going to get to go because it has the lowest virtual runtime. So only thread 1's actual runtime is going to increment by 5 because that's going to be our quantum. And so the new virtual runtimes are going to be, well, the other 2 threads stay the same because the system hasn't changed in any way. And your virtual runtime is now 20 units. So now we will select thread 2 to go next. Now, there's some interesting things that aren't taken into consideration here, or at least we haven't talked about. What about a thread that's new to the system? Because a thread that's new to the system would have an actual runtime of 0. Which means that its virtual runtime would also be 0. Does that mean in order to catch up to older threads, we're going to do like a giant burst of letting the new thread run? Well, theoretically speaking, that is what would happen, but that's not how Linux does it. So in order to prevent a bursty behavior, when a new thread arrives in the system, they assign it an initial virtual runtime somewhere between the existing minimum virtual runtime and maximum virtual runtime of the threads that are there. And similarly speaking, you could do the same kind of idea. When a thread becomes unblocked, you can adjust these numbers accordingly to make sure that we are more responsive to threads that are waking up due to a resource becoming available. And again, there's a paper for this. If you'd like to read it in greater detail, you can if you want. Maybe you're bored and you have nothing else to do, and if you don't want to, that's fine too. I'm not ever going to ask you anything about the contents of that paper, only about what we've got here. All right. So those are the 2 kind of big scheduling algorithms that are out there. There is another one that I really, really like. It's a really cool one. It's not in your notes yet, I do actually want to add it. It's called the lottery scheduler, and it's really fun, the idea behind it. The idea is that you're going to create a lottery, and a higher priority or higher weight thread is going to get more lottery tickets. So maybe you are a weight 100 thread, so maybe you get 1,000 lottery tickets. And then each time you have a context switch, you draw, and it has to be a guaranteed winner draw. You'll draw a lottery ticket. And then you run whichever thread has the lottery ticket that you just drew. So it's a way of implementing priority very, very easily, but it has no guarantees. Because obviously it's possible that you keep drawing the lottery tickets of really low priority threads. But it's a really fun idea for a scheduling algorithm that's actually pretty easy to implement, and it works reasonably well. Changes for the future of this course, shall we say. All right, so to wrap things up today, how do we deal with scheduling on multi-core processors? So there's two schools of thought to talk about. And I know there's 2 slides left here. I'm not going to look at them. We're going to talk about them with respect to this image that you see here. So school of thought number 1 is let's have a shared ready queue. So one scheduler, one pool. If it's multi-level feedback queues, one set of queues, and all of the cores are going to share that one scheduler, that one pool. So that's very, very easy to do. All that's going to happen is on a context switch, we select a thread from the system and we assign it to the appropriate core that requested a new thread. Easy. But big problem. So for 4 cores sharing this thread, it's not a big deal. But one of the things that you got to keep in mind is that you could have context switching happening on all of these cores at the exact same time, which means all of the cores would be requesting new threads at the exact same time. Now that would mean that we have contention for a shared resource. That is, we can only handle one context switch at a time, so we'd have to have a lock on this. And each of these other cores would have to wait their turn for their context switches to be handled. That's not a big deal for 4 cores. It's probably not even a big deal for 8. But what about something like Weta Digital, who has a render farm with hundreds of thousands? So you have hundreds of thousands of cores and they're all waiting for access to the shared ready queue. Easy to implement. But to be honest, this does not handle scaling very well. In fact, it doesn't scale at all. One of the other interesting downsides to shared ready queue is this idea of cache affinity. So we've talked about how the TLB on the MMU gets cleared for every context switch between different processes, which makes sense. Unless, of course, you use the PID field, so you get cache affinity, because cache affinity is this concept of the next time you run, there's still some of your data in the cache, which means that you don't have to do as many loads from physical memory as you would do if the cache was cleared. So you actually get a little bit of a performance boost. With a shared ready queue, each time you run, you could be running on a different core, and each core has its own set of caches, which means that data you cached in core 1 doesn't exist on core 3. And how long is it going to be before you run on core 1 again? And when you do eventually run on core 1 again, is that data still in the cache? And is that data even relevant to where you are? So the shared ready queue doesn't scale well, and it also has really bad cache affinity. The alternate solution is this per core ready queue. So essentially you could think of it as each core kind of has its own scheduler. And what's going to happen here is it scales really well because you don't have contention for a shared resource. You also get really great cache affinity because if you were running on core 1, then you're going to go back to running on core 1 because that's the only option that you have. So you get good scaling and you get cache affinity. That doesn't mean this is perfect, however, because there is a big problem with load balancing. In this example here, we have this core with 5 jobs and this core here with 1, which means this thread here gets a whole hour to run, and each of these get less than 10 minutes or less than 15 minutes to run. So it's not fair. It's entirely possible that you have 1 or 2 cores which are doing all of the work and the other cores are sitting idle. And in fact, in older versions of the Windows operating system, if you open the task manager, you could actually see that it wasn't handling load balancing very well, because there would be 1 or 2 cores that were at like 100%, and then your other 2 or 4 or however many cores you had would be empty. So in order to do this, we need to implement some kind of load balancing. That can be something as simple as when a new thread arrives, attach it to the core with the least load. That really depends on how often new threads are created. Another thing that you can do is you can periodically rebalance all the queues, or on a context switch, instead of preempting and putting you back onto your queue, you could put it onto the queue that is maybe the less balanced. Of course, one of the downsides of load balancing is that you're going to lose some, not all, of your cache affinity. All right, that is the end of the scheduling section of this course. So in our next episode, we are going to start discussing devices, and that is the discussion of how does your operating system actually interact with the physical hardware? How do you make the hardware do stuff, and how do you respond to the events that the hardware has done? And we're also going to be looking into how hard drives work and how SSDs work. And that's all coming up in our next episode next week. So we will see you on Tuesday.
Microsoft MS-DOS 5 upgrade training. This is the first time MS-DOS has been available as an upgrade. It's new. We're introducing something new. It's essential for all, the many and the few.
It's in your store. Ooh, Microsoft, that's who.
The MS-DOS 5 upgrade is a hit, and no PC should be without it.
No PC should be without it.
There are 3 key benefits to the MS-DOS 5 upgrade. Okay, girls, shrink it down. It's late at night, you're feeling right, working at your PC. Yo, your face turns green because the word on the screen is you're out of memory.
Oh no!
Give me 5.
Give me 5.
Give me 5.
Give me 5.
Upgrade to MS-DOS 5. Make DOS applications come alive.
Free more memory, can't you see? Spring those K's that got to be free.
Give me 5.
Give me 5.
Soothes any memory hogging beast, cause it frees 45K of memory at least. And that's why everyone who's in knows it's also the best DOS to run with Windows. Give me 5.
Give me 5.
MS-DOS is a mystery, admit it. MS-DOS 5 is easier. Here's how we did it. We gave it a graphical shell. That's the ticket. It's DOS with a prettier face. Yo, chicken.
Looking good. Like it should.
To copy files from drive to drive, just drag and drop. Give me 5. Wondering what command to use? Select from our drop-down menus.
The graphical shell. Do tell. The mystery's gone. Go on.
Plus online help, task swapper, editor, and lots of features to help you do more. One command helps you take the heat when you really mess up. Undelete.
The MS-DOS 5 upgrade is slick. Even from the network, install installs real quick.
Loads over any DOS on anyone's PC, but now you may be wondering how safe can it be?
I'd ask that, yeah, so would I. I'd want to know more before I buy.
Microsoft said, hear this rhyme, we'll test the upgrade big time.
Hit it!
Ran the biggest beta test in PC history. Hammered at it, yo, it ended most triumphantly.
No PC should be without it. No PC should be without it.
These MS-DOS 5 upgrade tales begin and end with mega sales. Here's the future, it's no dream. Customers in a steady stream. DOS has 60 million users waiting. Time for them all to be upgrading.
Everybody DOS now. Everybody DOS now.
MS-DOS 5 sounds easy when you tell it. The only thing easier is when you sell it. It's gonna be a cash machine for you. Upgrading is the natural thing to do. Gimme 5.
Gimme 5.
Gimme 5.
Gimme 5.
Alone or as an add-on, this product is a hit. No PC should be without it. MS-DOS 5 upgrade. Take that image further. It's like selling fries with every burger.
MS-DOS 5 upgrade with that. MS-DOS 5 upgrade with that.
No PC should be without it.
No PC should be without it. No PC should be without it.